Hi, class. We are going to get started with the very last problem solutions of the quarter. I hope you all have a wonderful Thanksgiving, and it's been a pleasure teaching you these past 5 weeks. I will send out an announcement when course evals are open, and I would really appreciate it if you take the time to fill that out. Thanks so much, and let's get going. Hi, class. So again, the final assignment for this week was we were going to look at the difference between linear and logistic regression. And so the way we do that is we were interested, our research question was, does dosage predict whether or not a patient's going to have an allergic reaction? So let's start off right away by looking at the linear regression, where we study the effect of dosage on whether or not a person has an allergic reaction. And the way we do that is we want to generate predicted probabilities. And what we're doing right now is something called the linear probability model. And the way we can save these predictions are we go to our save option, and I'm going to choose to save the unstandardized values of my regression. All right, so we're going to do that. And I also want to look at a graph of it. So let's do a plot as well. So we're going to do our dependent variable as our true outcome, and we're going to do our adjusted predicted values as well. Okay, so we're going to generate that, and let's see what that looks like. Now, what we see is that there's a pretty, let's see. That there appears to be a very strong relationship between dosage and whether or not an individual is going to have an allergic reaction. You can tell that because this R squared and R value are rather high. And so telling us that it's very predictive. And then what we can look at are the associated coefficients. Actually, that isn't quite giving us what we want. So let's do that regression again. We're going to do a linear regression on whether or not a patient had an allergic reaction based on dosage. Our statistics, we're getting our estimates. And the plot, let's ignore the plot for now. So we're just running a linear regression. And what we see is silly me, I was looking at the constant term and not the coefficient on milligrams. And what we see is that as a patient gets an additional milligram worth of the drug, they're more likely to have an allergic reaction. And what we're going to do now is we're going to sort of see how that model fits, our predicted values actually fit the data. So when we go to our data tab, let's see, where is our data tab? When we generated the predicted values in this way, we generated these two columns. And as you can see that there are some interesting things here. We're trying to predict the binary event of whether or not a person had an allergic reaction. And as you can see that a binary event should only have a 0 or 1 value, but we're actually predicting things that are above 1, and in some cases we're predicting negative events. And in these contexts, neither of them really make a whole lot of sense. And just to visualize this again, we're going to graph these, and we're going to go to our legacy dialog tab, and we're just going to create a simple scatter plot. And on one side, we are going to have whether or not an individual had an allergic reaction. And on the other, we're going to have the unstandardized predicted value. All right. And what you sort of see here is that it really has some quite counterintuitive results. That we've got probabilities that are relatively high that we're predicting, and people don't have allergic reactions, and we've got dosages that are relatively low in individuals have an allergic reaction. And it's really hard to tell from this picture if there's any relationship between dosage. There seems to be, like, for very high values, that's the case, and for very low values, there's a case. There's a relationship, but all these values in the middle are really hard to interpret. So what would be really great is if we could find a way to communicate that through the relative odds or probability of an event happening. And that's exactly what logistic regression does, is we try and predict the log odds of an event based on particular values. And so we're going to run the same analysis as a logistic regression. And we can do the same thing. We're going to predict whether or not a patient had an allergic reaction based on dosage. And when we go to save, we're going to instead predict probabilities. These map to the unstandardized values. We're also going to predict group membership. All right. Okay, and I know some of you had questions about how you read this logistic regression table. And what the first thing SPSS does is it goes through and calculates the accuracy of what's called a null model. That's a model if you just had to guess that every prediction was going to be the same. So in this case, because there are slightly more people who have allergic reactions than didn't, our sort of dumb model is going to assume everyone's going to have an allergic reaction. And as you might imagine, that type of model is not particularly useful. Now, when we go down to our logistic regression model, what we actually see is that we have we have a much better and more accurate model, so that it accurately classifies around 87% of the time whether or not a patient is or isn't going to have an allergic reaction. And in addition to that, we see that there's a strong and statistically significant relationship between milligrams and the probability that an individual has an allergic reaction. So in a lot of ways, the results here are very similar from the linear probability model and the logistic regression. But let's do a plot of these two predictions, and you can sort of see the relative advantages of them and the relative disadvantages. But first, I want to show you what the logit plot looks like. And we're going to go to options. Let's see. Sorry. We are going to do this as a legacy dialog. And it's going to be a simple scatter plot. And what I'm going to do is I'm going to plot on the x-axis, we're going to have our unstandardized predicted values. Actually, no, on our y-axis, we're going to have our unstandardized predicted values. And on our x-axis, we're going to have our logistic regression predicted probabilities. And what you can see is that they actually have that they are actually pretty tightly correlated. But what happens with the logistic regression is you see everything is nicely bounded between 0 and 1, whereas in the linear probability model, extreme values can go above that negative, that 0 can go negative, or they could go above 1, which is a little bit less interpretable. And again, this isn't a huge difference in this particular case. When we compute our bivariate correlations, we get a correlation coefficient that is quite similar. So in fact, the Pearson correlation is around 0.96, which is really, really high. But in other cases, in other models, this can make a really big difference. Now, one of the things I talked about in class was that there are many metrics for caring about the accuracy of a model. And in some cases, particularly in medical testing, you might not necessarily care if a test is super accurate. You might care about something called recall, meaning are you capturing all of the probable cases? Or you might care about something called precision, which is if a test comes back positive, it means it's very likely that an individual has the disease. Or you might care more about something called specificity, which is a measure of just how good is a test at telling you you don't have a disease, conditioned on the test coming back negative. And depending on the context, you might prefer one or more of these measures. And one of the things you can do to adjust your sensitivity to these measures is change the cut point, the predicted probability. So what I want to show you here is when we generated these predicted probabilities, you have not only the predicted probabilities, but the predicted group status. And you can see that the rule for whether or not something is a 0 or a 1 is based on the threshold of is the predicted probability greater than a half or not. So we've got this value that's around 0.46. And even though that's fairly likely, we're assigning that value to be 0. And we've got this value right below where it's 0.01, and we're assigning the predicted value to be 0. And as you might imagine, there's a pretty big difference. And like here, we've had a case where the probability associated with this dosage is 99% likely to have an allergic reaction. But then we've got values that are a little more marginal, so like 54%, and we're treating them as identical. And as you might imagine, that we could potentially learn more by varying this cut point. So what you can actually do is you can go through and generate something called a ROC curve, and that stands for receiver operator characteristics. And what that does is it plots recall or sensitivity against your test variable, which in this case would be our predicted probability. And then we assign our state variable, which is whether or not you have an allergic reaction. And we also have to define a reference class. So in this case, it's going to be 1 for whether or not a person had an allergic reaction. And I also want to plot and illustrate some of the cutoff points. Okay, so I'm going to do that. And then we get this curve. And what you can see here is that this red line corresponds to what is called a random guessing line. So that assuming that your model had no predictive power and you were just guessing based on certain cut points of the data, that's how you would do in terms of generating a model that's a certain level of sensitive and a certain level of specific. But because we know that our model and our predicted probabilities are quite good, that we can actually do a little bit better than that. In fact, what we see is that for the most part, our model is very sensitive. And also and can also be fairly specific as well. And you can see this by the statistic called the area under the curve, and that's generally what people use when they are evaluating sensitivity and specificity trade-offs. And the way you read this scatter plot is that for a particular value, so for instance, if we assign 0 to be the cut point for saying you have an allergic reaction, it's going to be perfectly sensitive and not at all specific, meaning that you're never going to say that anyone actually doesn't have the disease. But as you start to move up, you don't appear to lose sensitivity, at least for small jumps, but you do gain a little bit of specificity. And in fact, you can jump all the way up to, let's see, a 12% probability of an event and still have perfect recall, but still actually assign some exclusionary value to the test. And one of the ways that people sometimes like to balance this is by choosing a point based on the harmonic mean or the product of these two, of sensitivity and specificity. And if that's the case, you would probably end up somewhere in this region where both values are pretty close to 0.9. Oh. And again, I really encourage you to think about what diagnostic measure makes the most sense for you. Particularly in medical issues, there are a lot of contexts that are really important to think about. I think that's about it. I want to wish you all good luck with your last couple of weeks of fall quarter, and it's been a pleasure teaching all of you. I look forward to reading your final assignments. And again, please do not hesitate to reach out if you need additional help with statistical analyses. It's been a pleasure. Thank you so much.